We're going to be continuing section 12.2, zeros of polynomial functions, with a couple of theorems. The first one being the fundamental theorem of algebra, which states every function defined by a polynomial of degree 1 or more has at least one complex zero. So it's basically saying that every function has a solution, and it has at least one of those. The second theorem says number of zero theorem. Says a function defined by a polynomial degree n has at most n distinct zeros. So an example of this is that if I have something like x squared minus 6x plus 9, because the degree of this is 2, that means it will have at most 2 zeros. But that doesn't mean it has to have 2. It says at most it has to. And if you think about this, if this factors x minus 3, they end up actually being the same one. And this would be considered what Math Excel refers to as multiplicity. So you would actually have a double root here. So you would have 3, but it would be a multiplicity of 3. So 3 would be 2 solutions to the polynomial. Number 5 asks us to find a function f defined by a polynomial that satisfies the given conditions. And they tell us that the zeros are going to be -2, 0, and 1. But when you plug in 2 into the function, it equals 6. So hopefully our first instincts are, knowing that these are the zeros, would to be to do x plus 2, x minus 1, and then x plus 0, which would just simply be x. Now, if you think about what this polynomial is, it would be x squared plus x minus 2, so x cubed plus x squared minus 2x. And let's go back to this condition right here, f of 2 equals 6. So that states that if I put in 2, I should get 6. So 2 cubed would be 8. 2 squared would be 4, minus 2 times 2, which is 4, and 8. So that doesn't. We didn't get the number 6. So we're going to back up to the beginning. Having this x times quantity x plus 2 times quantity x minus 1, that's a good start. But what we need to happen is when I plug in 2, that this outputs 6. So I'm going to actually put a coefficient there because it's some number times this will give me this number. So what we're going to do is we're going to input these 2's to figure out what that a would be. A times 2 times 4 times 1. So that's going to give us 8a equals 6. So a equals 3/4. So now I can take this 3/4 and put it into that function. So the function that has these 3 zeros but does an input of 2, output of 6 would be f of x equals 3/4 times x times quantity x plus 2 times quantity x minus 1. We'll want to distribute that. So we're going to end up getting 3/4 x cubed plus 3/4 x squared minus 6/4 x, or you could reduce that to 3/2. One of the next theorems that we have is the conjugate zero theorem, and it states if f of x is a polynomial function having only real coefficients, and if a plus bi is a 0 of f of x, where a and b are real numbers, then the conjugate a minus bi is also a 0 of f of x. And again, if we think about what this really means is that, if we have this function that has only real coefficients, right? And one of the solutions is an imaginary number, what would happen is we would need to have the conjugate in there, because if you remember kind of back to the conjugates, a plus bi times a minus bi, um, these conjugates help to get rid of the imaginary number. And when you go to do the last one, I squared becomes a -1, so all the imaginary numbers disappear. So when we look at number 6, it says find a polynomial function of least possible degree, having only real coefficients and zeros of -2 and 3 plus 4i. Seeing this right here, this tells us right away that there is a conjugate imaginary number of 3 minus 4i for the 0. So we actually have 1, 2, 3 solutions. And those 3 solutions are going to look like x plus 2. And then this one gets a little bit trickier because it's a binomial. So it's x minus the quantity 3 plus 4i. And then x minus the quantity 3 minus 4i. And we want in a polynomial function, so we're going to have to multiply this out. So we're going to start by multiplying these two out, which is going to get a little bit complicated because it's not just a binomial. In reality, this is now a trinomial. So we've done this before. We've done this several times actually in the first few chapters. And we take this x and we're going to distribute it to each one. So we get x squared minus 3x plus 4ix. Then we're going to do that with the -3, distribute that. So I'm going to get -3x, and then -3 times -3 is +9, and then -3 times 4i is -12i. And then I'm going to do this with the -4i to each one of these terms. -4i times x is -4ix, and then we get -12i. And then finally, I'm going to get minus 16i squared. This should actually be a positive right here. Negative times a negative. All right, so this is going to give x squared minus 6x. The 4ix's cancel. The 9 drops down. These drop out. This then becomes a positive 16. So it reduces then to x squared minus 6x plus 25. We're going to now take this trinomial, multiply it by the binomial we originally had of x plus 2, and we'll distribute it out. We're going to get x cubed minus 6x squared plus 25x plus 2x squared minus 12x plus 50. And when we clean it up, it's going to be x cubed minus 4x squared plus 13x plus 50. This question right here, this last question we're going to do, goes back to the first video where we're given 1, 0 of the function, and we're going to have to use synthetic division to figure out the other zeros of the polynomial. So we're going to take 2 plus I, put in the top left corner, And again, I'm going to use those coefficients, and I'm going to start doing synthetic division. And this gets a little bit complicated just because we're dealing with binomials of I. And so we want to really kind of pay attention, and it gets a little bit complicated once you start multiplying those binomials. So we'll do that off on the side. 2 plus I times negative 5 plus I. So again, this is a negative 1. So it's a negative 11 minus 3I. And that's 2 minus 3I. Again, I'm going to FOIL that. We're going to get 7 minus 4I. We're going to save a little bit of work. But again, what I did is I would multiply 2 plus I times this 2 minus 3I. Then I'm going to get 8 minus 4I. And again, I'm going to multiply that one more time. And we're going to get 8 minus 4I times 2 plus I. And again, because it told us it's a 0 of the function, we're going to really hope that this ends up being 20, because that would mean that we did all of the math correct. So this will become a positive 4. Those will cancel out, so 20. And there we have the 0. Now this right here is actually our polynomial. And what we're going to do is we're going to use this as the new coefficients when we start doing the long division. And this is something different because the coefficients now have i's in them. And we're going to have to test for another 0. Now going back again to that conjugate theorem, if I know that 2 plus I is a 0, then 2 minus I is going to be a 0. So I'm going to go through this process again. We're 1 right here, and then this is 2 minus I. Now luckily those i's cancel out. I get negative 3. And then I'm going to get negative 6 plus 3I. I get negative 4. And when I multiply, I get negative 8 plus 4I. And that one worked out a little bit nicer. We didn't have to do any foiling, and that is 0. And luckily enough, I'm down to a trinomial, x squared minus 3x minus 4. And even better, this is factorable. X minus 4, x plus 1. And then my other two binomials come from x minus 2 minus I and x minus 2 plus I. If I was looking for the solutions, the other solutions would come from x equals 4, x equals negative 1.